So this is a non-empirical work, but I am going to try to make a few comments at the end on perhaps the relationship with the project here. So, and the issue here is thinking about modeling expectations formation and the feedback between that and market prices in this case. So the model is super simple toy workhorse model, 2 assets, stationary fundamentals, really no explicit market microstructure to speak of. So we have agents that are traders, and they're all chartists. They're forecasting returns. They're not sure about fundamentals or the beliefs of other traders, and so they're engaging in forecasting about what returns are going to be in the near future and acting on that. And what we're doing is exploring the consequences of the prediction technologies that are available to these agents for market volatility.
Hey, Chris, is the mic closer to you? Maybe?
Sorry. Yep. So, one takeaway from what we've done so far is that even if agents are paying a lot of attention to overfitting, somewhere close to the middle. Is that good? Okay, thanks. So even if agents have a fairly high degree of attention to overfitting, that it's unlikely to eliminate that overfitting and therefore eliminate destabilizing speculation. So here's a little bit of detail. So 2 assets, stock has a stochastic dividend, super simple, just a constant plus mean zero random variable. Epsilon bonds return is fixed and known. So if risk neutral trader, equation 1 here, risk neutral trader would be indifferent between holding the 2 assets if that particular condition were satisfied. In other words, if their forecast of the price and dividend next period divided by 1 plus the rate of return on the bond was equal to the price of the stock that they're buying this period. So they'd be indifferent between those 2 assets. So instead of having market microstructure, we're going to make things extremely simple here and simply have an arbitrage condition that says that the price today of the stock is just determined by the average forecast of the various traders in this market, right? So the agents do know the rate of return on the bond. They don't know the dividend process for the stock, so they're going to forecast the dividend next period and the price next period for the stock. So again, there's a very common and super simple setup here. We give the agents common prediction technology, so whatever one agent has is the same that all the other agents have, some modeling framework and some estimation method, and the estimation method may include model selection, regularization, cross-validation. Heterogeneity is going to be through asynchronous estimation. So basically, in each trading period, some subset of the population is going to re-estimate its model. And so you're going to get these cohorts of people who, through time, who adopted the same estimated the same fit model sometime in the past, and then some of those that did in whatever that period was will have re-estimated since then, right? So basically, the heterogeneity is simply, I'm different from you because I saw different data when I re-estimated my model. Okay, but we're all going to forecast with our current fitted models. Okay. So, what might these modeling frameworks look like? So here's a very simple one, polynomial regression. All of the agents use forecast rules that have the same polynomial autoregressive functional form. So an example is below in equation 4, so that would be a quadratic AR3. It does have cross products, so you can see that we're predicting this combination of price and dividend for next period using recent values of price and dividend, and including some squared values, including cross products. So there are 6 parameters, these A's here, to be estimated. And of course, we could use various agents could use various means to estimate an equation like that. We can also give them a polynomial, much higher order polynomial, right? So in other words, it could be that this equation has 500 parameters, 1,000 parameters. There's been a lot of early literature on just ordinary least squares in a problem like this, so least squares learning. Of course, if you use least squares to fit that kind of a model, you're going to just overfit the data, right, if you're not doing anything about overfitting. And so we can think about other methods like penalized regression, lasso, other types of elastic nets. So we're going to think about lasso. Lasso adds a penalty that shrinks coefficient estimates, but also sets many of them equal to 0. And so it generates sparse fitted models, reduces overfitting also by shrinking. Even the parameter estimates that are non-zero are going to be shrunk, and it can handle situations where the number of predictors is larger than the number of observations. So it could be that we have 500 predictors in that equation, and they're only looking at 200 periods of data, right? So that's allowable. But we could use other, particularly for a larger, more complex polynomial, we could use other kinds of search algorithms. Okay, so all I'm going to do right now is compare some results from running this model when agents are estimating with OLS, and they're estimating particularly that particular polynomial rule there, number 4, right? OLS versus lasso. And so the red, let's see, I can come out here, I guess. Right, so when we start over here, so these are the OLS coefficients for those 6 coefficients A in that equation, and you can see that there's a ton of movement in those coefficients relative to lasso. Still a lot of movement, but also a lot of sort of inactivity, where essentially what any trader who estimated that model, say at this time here, is saying, oh, I don't see a whole lot that's predictive here in the recent data, and so I'm going to set all these coefficients equal to 0, and I'm just going to estimate a constant. So what's that? That's just taking an average, essentially, of the recent data and saying that's my forecast, right? So there's not a lot going on in terms of forecasting here. And so if we go over here, there is, of course, over here, there's a lot of movement in forecasts over here. And so here we see that the lasso estimates are giving you very, very little volatility in returns in a period like that, whereas the OLS method is giving you lots of variability, lots of volatility in returns. And so you're going to get these punctuated periods of volatility from the lasso estimation runs when agents who are re-estimating see what they think is predictable movements in the recent data, and that just happens occasionally compared with OLS. Okay, so this kind of pattern of apparent sort of pockets of predictability is something that you see empirically in literature that's looking both at raw financial data, but also at the behavior of folks who are trying to predict those movements, and you're seeing that with the lasso and not with the OLS. So the lasso is giving you, so let's look at one other thing here, which is, so this is occasionally, you don't just get volatility, you get bubbles. So we say, well, if the price moves away from essentially the fundamental value price in the model, then we're going to call this a bubble. And with OLS, since there's all this overfitting, there's just tons of bubbles going on here. And this is varying memory in this direction, and this is varying the rate at which the traders are re-estimating. So if I have 90% of the traders re-estimating in a particular period, then you're up here at 0.9. If you have 10%. And so in general, the slower the learning is, the more stable things are, the fewer bubbles, the lower the incidence of bubbles. And the larger the memory, the lower the incidence of bubbles. This is just because with slow updating, you get more heterogeneity in the markets, and everyone's not jumping onto the same new information and trading on it. Lasso, you just see a much lower, similar kinds of patterns, but a much lower incidence here. And so again, it's not surprising because we've cut way back on the overfitting, and and so there's only going to be fewer episodes where we're going to be likely to see a bubble forming. Okay, so lasso, and I'm using k-fold cross-validation here again to fit the hyperparameter in the lasso estimation, but it's generating fairly simple, interpretable, fitted prediction models. It's substantially mitigating overfitting and consequently reducing volatility and stability in the model. However, it's not entirely eliminating overfitting. So there's this survival of apparent pockets of predictability here, again, as documented elsewhere in the literature. Now, what would happen if we looked at other kinds of estimation methods, right? Other kinds of machine learning methods that are aimed at, again, mitigating overfitting, because really everything that's happening here is happening because of overfitting. The structure of the model is so simple, right, that these agents could just in principle be predicting, oh, the price is going to be the same all the time. And if they did, they would learn the sort of the equilibrium price of the model, and you wouldn't get any of this volatility. Well, so we've tried a few other estimation methods. We're in the middle of working on others as well, but it's unclear whether that's going to push us in the direction of more opacity or less opacity. In other words, are these models, once they're fit, going to be easily interpretable or not, right? So if we use neural nets and those actually end up doing better, that's more opaque, right? And if we, so there are methods that could push us in either direction. So one of the nice things about about Lasso is that it's giving you these nice sort of easily interpretable results, right? But the agents really just care about predictions. So this is getting to Josh's point yesterday, right? This is a model in which agents are not necessarily trying to understand what's going on, they're trying to predict, right? And so if indeed what they really care about is prediction, then their interests may be at odds with us as the modeler, right, who wants to really understand what's going on in the model. I
wouldn't put it quite that way. I'd say you're trying to explain the overall phenomenon with agents who are individually predictive.
Correct.
That's fine.
That's correct. So
micro specification.
Yeah. So this is sort of my my conclusion here is these agents tend to overfit the data. We've created a very, very simplified environment to study overfitting as a driver of volatility and stability. We're really just telling stories here. This is not an empirical model at the moment, but you know, one of the things that we're seeing is that if the agents actually have the choice, they may very well prefer, right, more opaque modeling environments or generate more opaque fitted models. And you know, I think this is a general issue that we're going to see in a lot of different environments. I mean, if you think about the use of algorithms, predictive algorithms to curate and to advise, that's happening all over the economy, right? That's happening. So, you know, plugging in a predictive, a sort of black box predictive model may be something that we see ourselves doing more and more of as we go forward and we're modeling social and economic activity. Okay, so, and it's not clear to me that that's a fundamental problem for, I see, for inverse generative social science. I wasn't sure whether Josh would agree.
I think it's a good topic.
But that's where I'll leave it. Okay.
Yeah.
So, any questions?